I will share my screen.
So please go ahead.
Okay, I will do that as soon as I find the play button. Of course, it is hidden behind all the Zoom things. Okay, so thank you very much for this opportunity, and thank you to Daniela for the great talk to give some introduction to some of these things. Rather than focusing on a particular model, here I'm going to talk a little bit more generally about these nuclear anomalies that have served as some of the motivation for Daniela's talk, and this is some work done in collaboration with people here at UC Irvine, Jonathan Fang and Tim Tate. So just to get kind of a brief review of where these signals are coming from, this is from this nuclear collaboration in Hungary, the ATOMKI collaboration, and the experimental setup is a pretty simple one, where they have some proton beam. It comes in here. I hope you can see my pointer. It strikes a target here in the middle of the experiment. And the idea is that this produces some excited nuclear state, which we'll typically call something like N star, which then decays to the ground state and emits an E plus E minus pair, which are then detected in these detectors here at kind of wide angles. So that's the rough story of where these excesses come from, the ones that Daniela showed where they are seen is in the angle between the E plus E minus pairs. And so what I want to talk about is kind of the consistency, or a kind of question of, are these two signals that we've seen now, or that have been presented in both the beryllium-8 and helium-4 situations, are these two signals consistent with each other? And if they are consistent, what kind of constraints do they put upon the different types of kind of particle physics interpretations of what these signals may be? So the first thing to point out is that in the rest frame of the X, as we try to understand these signals, and neglecting the mass of the electrons, the E plus E minus pair, of course, in the rest frame of the X, the pair is back to back. And the only thing that distinguishes one decay from another is the angle it makes with the kind of the boost back to the X direction of motion in the lab frame. So of course, if the boost is parallel to the E plus E minus pair, then when you go to the lab frame, they remain back to back, just with some variation in their velocities. On the other side of things, so this of course would be when they're back. In this case, this parallel alignment would be the maximal angle between the E plus E minus pair. If instead the boost is perpendicular to the E plus E minus pair, then they'll both be bent towards the direction of travel some amount, and this would be some minimal angle that is made between the two particles. And so you can see that there is some, if you have some particle decay like an X, that you're going to have some width or some range of opening angles between the E plus E minus pair that you would look at. And what's more, you find that this distribution of angles is peaked toward the minimum in this way, depending on what the, just from the kinematics. This is, I should say, neglecting the mass or neglecting the spin of the X, which could have some small effect, but the leading order, this will be the story. And so then at the level of simply kinematics, you can ask what's going on with these excesses that are seen. So if you look at, for instance, the beryllium case, you'd see that the peak of the distribution is around 140 degrees, and you'd expect then kind of the bulk of the signal to be there. And indeed, as you look at the beryllium results, see that around 140 degrees is where you see the peak of the distribution here. And then for helium, of course, you would not expect to see the peak in the same place because there's a different gap between the ground state and the excited state that you're looking at. And here the maximal mixing, or the maximal angle between, sorry, the minimum angle between the two particles would be closer to something like 112, 114 degrees. And indeed, you see here in the helium case that the peak in the distribution is no longer at 140, but closer to something like 115 or so. So that there's there's a consistency with that idea of a particle being produced. And also, this is something that gives some confidence that this effect is not just some kind of experimental systematic. If you're worried, for instance, about the setup of the detector, the distribution of the telescopes is causing some kind of systematic effect, then the fact that the excess moves like this when you go to different systems is comforting, because that's not what we'd expect a systematic effect to do. Maybe to say this in one more way, you can imagine plotting this minimal angle between the E plus E minus pair versus the splitting between the ground state and the excited state, and then simply plotting the results from the different experiments, or from the one experiment, but using two different targets. And you can find that the measured kind of measured angular center both fall along kind of consistent masses of around 17 MeV. And this also brings up some other ways that you might think to test this hypothesis. By using a variety of different targets, you could then continue to see, or do we continue to lie upon this same figure, this same curve contour in this plot. And so what I would claim then is that the two ATOMKI signals pass this very, very basic check of kind of kinematical consistency, that the particle looks like a particle being produced in these two different situations. But of course, what we demand is much more than simple kinematical consistency. We need to see that there's some kind of particle dynamics that is consistent between these two, if we're going to claim that this is the same physics involved, or the same particle interpretation. Ideally, it would be nice if we had a nice, relatively simple model, such as Daniele's, to tie all these things together. And what I'll kind of point out in this talk is that such consistency is pretty non-trivial. And so even just having these two signals, these two different experimental results, is somewhat constraining and kind of pointing in specific directions that are worth more investigation. So what we'll do is we'll kind of layer on small amounts of physics, if you like. We started off with just kinematics, and now we'll just lay a little bit of quantum mechanics on that, spin and parity. Because the ground states are all scalars of these different nuclear states, and the different excited states of the two different situations have different spins and parities. For instance, in helium, there are actually two excesses that could be excited. One is a 0 plus and one's a 0 minus. In the beryllium case, it was a 1 plus. But you can imagine looking at all the different possibilities for a new X particle, an X boson, being a scalar, a pseudoscalar, a vector, or an axial vector, and kind of seeing what the possible decay dynamics would be as constrained by spin and parity. For this case, we've also included, and we'll mention a few times briefly, carbon. And we only bring in carbon because it happens to have an excited state. It's about the same mass, I think 17.23 MeV, which is a vector. So it kind of fills out this table very nicely. But if carbon is not a useful experimental target, then the analysis would translate very easily to other vectors. But already we see something very interesting here. If we look at the possibilities for what the X might be and the different targets that you could consider for the excited state, the kind of first and most obvious one is that if you looked at a scalar X, that it cannot explain, doesn't have the right parity to explain the beryllium results, and so we just kind of exclude it right off the bat. However, if you look at the pseudoscalar and the axial vector, then you notice that in the beryllium case, the decays are dominated by either the P or S wave, respectively. But in the helium case, they're dominated by the opposite, the S and P wave. And so in the most kind of naive estimation, you might say, oh, I would expect these two decay widths to be somewhat different because different partial widths are dominating decays. Whereas for a vector X, both the helium and the beryllium decays are P wave. So you can get a little bit of information from just spin and parity. It's a nice way to organize thoughts, perhaps. But again, it's not all that we want. We really want to look at actual decays. And so for that, we'll use an effective field theory so that we can really incorporate, particle dynamics and try to explain these more carefully, look at different decay amplitudes and decay widths. So for that, we will describe the different nuclear states, each one by its distinct point-like quantum field, and look at the transitions between them in this EFT. But we want to then be able to use those results, all those different decay widths, to compare with other experiments. And so for that, we'll match to also nucleon couplings to the X boson, because many of the other experiments, such as those that Daniela was showing us, they really care about the nucleon couplings or the quark couplings, rather than the couplings to various nuclear excited states. And so we'll have a matching between the kind of nuclear EFT and a nucleon EFT in ways that I will show you. So let me start with the pseudoscalar. And I will point out here that the pseudoscalar that we're looking at is not really an axion-like particle like the one that Daniela showed. And so it's a nice complementarity between our two talks in this way. But if you imagined a pseudoscalar which was not derivatively coupled, then it might couple to, we could parameterize its couplings to protons and neutrons in this way with just some unknown coupling. But this is perhaps not as useful for looking at nuclear states. And so you can rewrite that in terms of a iso-singlet current and an iso-triplet current, where the iso-singlet current, of course, takes you from one state to another state of the same isospin, whereas the triplet current will change your isospin by one. And these are simply a rewriting of these two currents in a very simple way. Since then the beryllium decay is isospin preserving, both the excited state and the ground state are, to kind of a good approximation, isospin 0. Then what you have is you could rewrite the amplitude, the matrix element, from going from the excited state to the ground state plus the x, in this simple way, where you've factored out the couplings to the iso-singlet current and have some matrix element between the excited state and the ground state in terms of that current, something that you can imagine is fairly universal and could be extracted from either experiment or maybe lattice simulations. So then we take this and we want to compare this kind of nucleon understanding to our effective field theory for the nuclear states. In this case, the dominant decay amplitude or dominant decay operator is simply this one. I have a pseudoscalar x. I have an axial vector excited state, and so with a scalar ground state. And so this is the parity preserving, the leading parity preserving operator for this decay. And then in this case, using this operator, you simply evaluate the same matrix element where we've included the same factor of the couplings on the front for ease of comparison. And this allows us to relate then this unknown matrix element to, if you like, the Wilson coefficient that we would put in front of the operator in this way. And so the C's that will show up throughout this analysis, these coefficients are meant to kind of encapsulate all of these nuclear effects and expected to be kind of very roughly order 1. So we've done that for the beryllium case now, and we want to move on to helium. The procedure is very similar, where we have, again, an iso-singlet current that's involved, but now a matrix element between the excited helium state and the ground state in the helium-4 system. And then we have a different operator which mediates the decay in the helium case, which, as Daniela points out very appropriately in her paper, is not derivatively coupled and so does not apply to axion-like particles that she's interested in. But let's set that aside for now. For other types of particles, this would be the dominant decay. And you would then calculate the width both in the helium case and the beryllium case, and then, for instance, take the ratio. And what you find, without much trouble, is that you have some ratio of these nuclear matrix elements. You have some dependence on the scale at which you're kind of normalizing all of your elements, which we take to be roughly the GeV scale. And assuming these things are order 1 and about GeV, then you find that there's a factor of 1,000,000 between the size of these two widths, which does not seem to agree with the width presented by the ATOMKI collaboration, where they gave the two decay widths to be roughly order 1. There's a little asterisk on that, a little caveat that I'll come back to later. But roughly, this analysis would seem to disfavor the idea of a non-derivatively coupled pseudoscalar-like particle. Now, what happens, of course, in Daniele's case, as she also we proceed with. The same can be done for an axial vector along the same lines. Of course, the current is slightly different, but not in any meaningful way. And then you can make these matching calculations and comparisons both in the beryllium case and in the helium case. And then again, for the different operators that dominate the decays, and then find again the ratio of the two. Here you find again up to some unknown coefficients of these currents and the scale of lambda, that there's about a factor of 100 between the two decay widths, which again does not seem to align so much with experiment, but considering the uncertainties is perhaps borderline consistent. And so perhaps worth some further interest. We point out here also that if you looked at a different situation, carbon has not been measured. There's no excess seen in carbon, hasn't been studied in this way. But if you were to see such an excess in carbon, it could provide some additional insight into the coupling structures, because the carbon decay is from an isotriplet decay, going from a triplet 1 state to a triplet 0, or a isospin 1 state to an isospin 0 state. And so in that ratio, you get more information in the sense that you can start to tease out the actual particular couplings to the proton and the neutron. I just point this out as something interesting going forward if you look for other ways to probe these potential system, if you want to extract individual couplings, and looking at isospin, non-zero isospin states could be interesting. Finally, we look at the vector case. In the vector, we actually have some additional handle to say things a little bit more carefully, which is that we can relate the decay widths of the vector to decay widths of the photon. They go to the photon. And since they both couple through vector couplings, we can often divide out the unknown nuclear matrix elements and say something a little bit more specifically, a little more precisely about the couplings. And so toward that end, we'll simply include one factor of the electric coupling to both the proton and neutral currents, so that we can write them now in this same way with the isosinglet and isotriplet currents, but including a factor of this coupling so that we can easily compare with the photon current, which also has this factor of E over 2. Then we proceed along the same lines, of course. We can calculate this, the matrix element for the decay, and find some relationship between these unknown matrix elements and the Wilson coefficients. So here we're looking at the beryllium case. And in this case, the dominant decay operator for the X boson is this one, where you have, because the excited state is an axial vector, and the ground state is a scalar, you need to couple through the epsilon tensor to a vector X. Now, what is nice about this is that, of course, it's because of the antisymmetry of the epsilon tensor, it's very easy to then rewrite this if I were to replace X by a photon with just the field strength. All you need is a factor of 2 because of the asymmetry of the epsilon tensor. And so essentially the same operator is determining the decays both for a vector X and for the photon, which means it's very easy to relate the two decay widths. When you calculate them, you find that up to basically phase space, the only difference goes like the coupling squared. So this is kind of the most simple-minded result. This other group showed back in 2016, when these results were more brand new, that there is in fact likely some isospin mixing and breaking in this system. And if you incorporate those effects, you get different dependencies on the different linear combinations of the couplings. But again, the form of the coupling is very similar. So that's in the beryllium case. Let's turn now to helium. In helium, we play the same game, of course. We can calculate what the decay width is with our dominant operator here for the X boson. However, it's clear that if I replace X by the photon field, that would not be gauge invariant. In fact, the leading transition, photon-like transition, is this one for the so-called E0 transition, which is an interesting one because it's actually not a decay to an on-shell photon, but rather through an off-shell photon to the electromagnetic current. As you can see, simply by integrating by parts from either one of these derivatives, you find that using the equation of motion for the photon, that the current is what shows up, and you get something like this. So this takes a little bit more care as we want to relate the two different decay widths, but it's not so bad. We can simply take the E0 transition type of operator, but replace F mu nu with, if you like, the X field strength and X mu nu. And then when we integrate by parts, we can use the equations of motion for the massive X boson, and we find a part of the operator, kind of the dominant part of the operator that's not suppressed by the small couplings of the J current, has the form of the operator that we used to calculate before, but with this coefficient mx squared over lambda squared. And so we see that we can simply relate the two Wilson coefficients, or equivalently, we can relate the two matrix elements by this way through mx over lambda. And so finally, at the end of the day, we can then relate this two-body decay of the X from the excited state to the X in the ground state to this three-body decay to the ground state and an E plus E minus pair in this simple way and get that result. And because the width down to in this E naught transition has been extracted from inelastic scattering in the helium transition, then this corresponds to if you like, a prediction with some error bars that come from this uncertainty on what the helium widths would be that correspond to the beryllium widths. So what I mean is that you can take the beryllium results and you can look at the constraints on the beryllium results and then say, well, what types of measured helium widths would agree with that? So what are the bounds on this type of vector particle? Again, this is back to this work by this other group, where they find that the most constraining bounds for the proton coupling come from pi naught decays to a photon and some other new boson, which constrains the proton coupling to be smaller than about 10 to the minus 3, whereas there's a weaker bound on the neutron coupling, comes from lead neutron scattering. It's about the order of 10 to the minus 2. And as the beryllium results favor a kind of a total nucleon coupling of E plus or epsilon plus epsilon n, epsilon p plus epsilon n, of close to 10 to the minus 2, this would imply then that the coupling to the neutron is much stronger than the coupling to the proton, and so it's been called a protophobic vector. So again, while Daniela's axion was piophobic, this vector would have to be protophobic. But then we can, with that understanding, we can compare the decay width that is predicted from the ATOMKI collaboration, from their results, with what we see from the beryllium results, and those are given in these plots. So in the top line here, these are the plots assuming no isospin breaking or mixing in the beryllium scenario, and the ones on the bottom are with isospin breaking and mixing. The plots on the left are for the kind of maximal value of the proton coupling, and on the right for the minimal value, as far as having the opposite sign. And so then we can just see, we can compare the shaded region that's preferred by the beryllium excess to the contours, these black contours, which are in the ratio of the X decay width to the E naught decay in the helium case. And so what we see here is that roughly, if we look at over all possible plots, we're running from about a value of 11 down to something more like 1. And so this we would say is kind of the range of possibilities that would be consistent with the beryllium results. When that comparison is then made, we have this 1 to about 11 times 10 to the minus 2 times E naught, because this was our normalization for those contours. And so we get some particular range of widths that we see here. But what's interesting is that that range does overlap with what we get from the ATOMKI measured result. If you take the width that they give in the helium paper and you fold in the uncertainties from the E naught transition, then we do have an overlap between these two, which is pretty non-trivial. Let me emphasize some of the differences between these two setups as far as experimental setups. I mean, they are the same types of experiment, but the dynamics of the two systems are quite different. In the beryllium case, you're looking at an axial vector excited state. In the helium case, it is a scalar excited state. The beryllium was run right on resonance for this excited state, whereas the helium was run in between two resonances. The operators between the two are quite different. The types of decays you're normalizing to, one is 2-body, one is 3-body. One has isospin mixing, one has no isospin mixing. The fact that there is some agreement between the two is pretty non-trivial. Now, before I end, I'm not quite sure how much time I have, but I'm guessing it's very little. I want to point out that there's an opportunity with the helium case. The ATOMKI collaboration, when you read their paper for the helium case, they were very interested in exciting this pseudovector state, the 0 minus, the higher excited state. But they were unsure of kind of the backgrounds as they went to higher and higher beam energies. And so they ended up just running lower down, if you like, on the Bright-Wigner distribution. So anyway, they ran in between the 0 minus and the 0 plus states. And then they use the E naught transition, which comes completely from the 0 plus state, to normalize the results they hoped they were getting from the 0 minus state. So what is something you can do, of course, to check some of these hypotheses about what type of particle might be responsible for these decays, is simply to scan along the energy. So you can probe different parts of these Bright-Wigner distributions. In particular, you could run right on resonance for the lower state. And if the particle is more vector-like, then you'd expect to see some enhancement in the signal, considerable enhancement. Whereas if it's something that's axial vector-like or pseudoscalar-like, then you'd expect the signal to degrade as you scan this way, going down the Bright-Wigner. More generally, if you consider an X particle that has maybe some couplings that are vector-like, or some that are axial-like, or some couplings that are scalar-like, with some are pseudoscalar-like, then you can simply say that if I take the ratio of kind of the cross-section of X bosons to the ratio of produced E plus E minus pairs from the E naught transition, then I expect, as I scan in energy, that I have a piece that has no energy dependence because it's coming from the 0 plus state, just like the E naught is. And so no matter where I move on the Bright-Wigner distribution, it's the same point for both of those states. And so this ratio would be fixed. Whereas I'd have another piece that's sensitive to the ratio of decay widths from the 0 minus to the E naught state, which depends very much on where I am on the two different Bright-Wigners. And so as you scan, potentially as you were to scan in energy in this experiment in the helium case, you could be able to pick out couplings to both of these states if they exist, or to show that the couplings are only to either the 0 minus or the 0 plus. So as I think I'm out of time, let me go fast here, but just to point out that these experimental results from ATOMKI are very interesting, kind of suggestive. And what we have shown here is that even with these just two very preliminary results, or these two kind of first results, you can say something very interesting about the parts, or the kinds of particles that may be consistent with this structure. We see that a spin-0 particle, which is not derivatively coupled, is in tension with the results, though a vector-like particle seems like it could possibly explain both of these results. We are, of course, looking for other groups to reproduce or refine the ATOMKI results, as well as further theoretical and experimental analysis that could zero in on a more particular model that could explain these things. So as we look for the future, I guess I will leave things there. Thank you.
So thank you, Chris. If there are any questions, please go ahead.
So, can you hear me?
Yes.
Just to be clear, for the helium case, you use an off-shell decay. Could you go back to that?
Absolutely. Yes. So in the helium case, there is no on-shell photon decay from the 0+ state to the ground state. There is if you like, an electromagnetic decay through an off-shell photon to an E+ E- pair. But there's never an on-shell photon involved. So we do want to have comparison to this vector-like coupling. And so this is the decay that you want to use to get those unknown matrix elements to divide out. But unfortunately, it's not as simple as in the beryllium case where it was, two different two-body decays that were compared.
Oh, sorry. This is just the statement that there are no 0-to-0 transitions, right? With a vector.
Right. Mm-hmm.
Okay. I see. Okay, so you just gauge it against the internal pair creation transition.
That's right. That's right.
Okay.
That seems to be the simplest thing that we could do.
Okay, I was confused here for a sec. Thank you.
No worries.
So Daniele, you have your hand up. Do you have a question?
Yes. Hi, Chris.
Hi.
Thanks for the nice talk. My question is first about, you mentioned the scanning of the energies for helium-4. That is a suggestion for the ATOMKI collaboration to do.
Yes.
I mean, why haven't they done this? This seems like something that they would have done, given that they did that for beryllium, right?
Right. So, of course, one can never know what anyone else is thinking, but we did talk to them about this. If you read their helium paper, they are really interested in the 0- state. They talk about really wanting, all of the analysis kind of assuming that the X particle is being produced from the 0-. And so I think the issue was, that they might want to scan through that resonance, but they weren't confident that they understood the backgrounds around that resonance. And so they kind of just did the best they could by being somewhere down here. During the course of our writing this paper, we did talk to them or corresponded with them and said, could you run on resonance down here? Because we actually think it's kind of interesting to do that. And so as far as we understand, they took that as a good idea and have started some kind of the preliminaries of background estimations for that resonance. So that was several months ago. But yes, I'm hopeful that they will, as you say, scan through the lower resonance just to see what we can see.
Okay. I have another question. Sorry for asking this question,
Sure.
but I'm curious about the paper by Zhang and Miller. The recent
sure.
paper. Yeah, do you have any, I am not an expert, I don't claim to fully understand that paper, but do you have a comment on that?
For sure. So just to kind of put everyone on the same page, there is a recent paper by Zhang and Miller where they make this claim that in the beryllium system, if you have actually a protophobic X boson, then there is the non-resonant production mode for the X is very large for some reason. And so you would not see this, you would not see the excess go up and down as you scan through the resonance in the way that the ATOMKI collaboration saw. They have this very nice plot. Do I have it at the end of here? I might have it at the end of here. Yes. So the ATOMKI collaboration in beryllium, they scan through the the resonance, and you can kind of see at different energies, you see the bump is there or going down or missing as they scan through. And what Zhang and Miller claim is that this would not happen for a protophobic boson, because the actual dominant production mode is through this non-resonant process. So you would just continue to see the excess. We are still trying to understand that. It is written in a language with which we are less familiar. We've talked to one nuclear theorist about it who also has some concerns about some of the assumptions that they made, but we don't know enough to say something one way or the other. I will say that we are actively trying to reproduce their analysis in kind of a more EFT language that we understand, so we can either confirm or, if not confirm, better understand the claims that they are making. So yes, it's definitely something I probably should have mentioned, that it's possible that this is another way of completely eliminating the protophobic vector interpretation. But I would say that the jury is still out so far.
But then it wouldn't say anything about the helium case, for that matter, right?
Right. They did not include an analysis of the helium case. My guess, yeah, I don't know exactly why that wasn't included. Maybe it's because beryllium was enough.
I mean, the beryllium, as far as I remember, when I was working on this, the beryllium is a complicated system, right? It has it's a symmetric nucleus, just like the helium in that sense. It's 4 and 4, but also there are issues like with old papers. That's why I think they scan over the angle, right? Over the energy. That there is something with the forwardness of the outgoing products. That there's something weird going on there, that they have to gauge for that. I don't really remember. I thought maybe you'd remember, but maybe that's what Zhang and Miller are alluding to. I think there's like an old paper by Goldring from 60s, maybe 70s. I'll look it up. But anyway, yeah, there's an issue with the forwardness, I think. So maybe it's worth looking at it.
Yeah, I'd certainly say so. What we're hoping to do is to look at kind of, as I said, a kind of an EFT type of analysis of the production modes to see what things should dominate and how you can relate the operators that produce the different kinds of production modes. Because they seem to, kind of like what we are doing, making an association between production of photons and the production of this massive vector. But for some reason, in the protophobic limit, and it seems to depend very strongly on the protophobic limit, that you get this non-resonant enhancement over large energy scales. So we're still working through it.
Thanks.
Mm-hmm.
So are there any further questions? If not, thank you very much, Chris and Daniele, for the talks, especially for giving them at breakfast time. Thank you very much.